All right. Hello, general chemistry. Welcome to this description on one of our labs with the spectrophotometer, the colorimetric determination of an equilibrium constant. It's going to be broken up into two parts. Part one will be getting to a calibration curve. So, what you may see when you have your stock bottle of iron 3 nitrate in a tenth of a molar nitric acid, the starting concentration being 2 times 10 to the negative first molars. If you take 10 milliliters of that stock solution and then dilute its final volume to 50, that would change its concentration to 0.04 molars of iron nitrate, iron 3 nitrate. Now, the nice thing is, what we care about is the iron 3 plus ion. Well, that will be a one-to-one breakdown when that iron nitrate breaks up into respective ions. Therefore, 0.04 molar iron nitrate means that we're working with 0.04 molar iron 3 ion. When we get into the concentration of sodium thiocyanate in 0.10 molar nitric acid, this will be, that is just what the stock bottle says, 2 times 10 to the negative third molar sodium thiocyanate. Now, in reality, we're going to be diluting this to different final concentrations. For part one, to find the concentration of sodium thiocyanate, take that starting molarity, 2 times 10 to the negative third, multiply it by the amount of milliliters you take of that stock solution, and then divide by 50 milliliters to get your new concentration of sodium thiocyanate. And like in the case of iron nitrate, the ion we care about is the thiocyanate anion, which once sodium thiocyanate breaks apart, you'll have a one-to-one. For each sodium cyanate, you'll have one thiocyanate anion. Therefore, this formula also tells you the exact concentration of thiocyanate that we will be working with in part one. For the calibration curve, we need to know the thiocyanate concentration. So what matters is here we're using either 0, 1, 2, 3, 4, or 5 milliliters of our 2 times 10 to the negative third molar thiocyanate concentration. And therefore that gets us the respective concentrations of 0 um, through 2 times 10 to the negative fourth molars of thiocyanate, or whatever exact volumes you do end up retrieving for those specific solutions. What we notice here when we compare the concentration of iron ion, of iron 3 ion, and thiocyanate -1 anion, each solution is going to have 0.04 molar iron ion, but the highest that our thiocyanate gets is 0.0002. What this is meant to say is that for part one, we have such a large excess of iron ion that even though this reaction is traditionally in equilibrium, all of that thiocyanate ion is going to be reacted due to it being a limiting reagent. This allows us to treat this particular set of trials as one directional instead of an equilibrium. And since thiocyanate is our limiting reagent, we know how much of that we have to react. We'll just assume that all of it reacts to form complex, our iron complex, iron thiocyanate. So what we're doing is treating this reaction as iron 3 in the aqueous state and thiocyanate anion in the aqueous state reacting to form iron thiocyanate. And because thiocyanate and our complex are a one-to-one ratio, whatever concentration of thiocyanate we have to react, that's the end concentration of iron thiocyanate we'll have when we are measuring absorbance and percent transmittance. When you get your absorbance values in this particular experiment at 447 nanometers, you'll graph a calibration curve of absorbance versus your iron complex concentration. The units for absorbance are usually treated as AU or arbitrary units, and for a graph, it's customary to include the wavelength that absorbance was measured at, in this case 447 nanometers. And you'll compare that to your iron complex concentration, molarity, or moles per liter. This particular experiment, we're at a range of concentration where we are in a linear region of the relationship between absorbance at 447 nanometers and our complex's concentration. You'll use that to get a trend line for a linear relationship. Usually in these experiments, your regression value, your R squared value is close to 1. These are very linear, very typically. And whatever linear trend line you get, it'll be in the common format of y equals mx plus b. And in reality, what that is just our absorbance equal to that slope value multiplied by the current concentration of our complex plus the intercept. And we'll save that equation for part 2. In part 2, we are now going to be determining an equilibrium constant, and for this, we have the iron concentration at the start of our experiment. We're working with, again, 2 times 10 to the negative third molar iron nitrate. We will take 5 milliliters of that and dilute it to a volume of 10 milliliters in each of these solutions, which gets us a initial concentration of iron 3 plus ion, cation of 0.001 molar, and the initial concentration of thiocyanate anion in part 2 that will range with whatever volume we take of our 2 times 10 to the negative third molar thiocyanate stock solution. Whatever milliliters we take of that, and then we divide that number by 10. For example, for solution 1 in part 2, where we take 0 milliliters of our 2 times 10 to the negative third molar solution of thiocyanate, that gives us a initial concentration of 0 molar thiocyanate. And in the case of taking 5 milliliters of that solution for solution 6, we'll end up with 0.001 molar thiocyanate initially. Now, in part 2, we do not have one reactant substantially in a higher concentration compared to the other. These are actually more comparable. They're not weighted toward one side. Therefore, we're going to actually have an equilibrium reaction occurring between the reactant ions and our product complex. Because there will be an equilibrium, we can actually calculate a KEQ, an equilibrium dissociation constants, and we'll need to use our ice tables and our trend line formula from part 1 in order to calculate the relevant values we'll need for KEQ. Something very important to note is whenever you have an equilibrium reaction, always give your solution some time to reach an equilibrium after you've already prepared them. For this experiment, give them about 5 minutes after you prepared them to allow them some time to reach an equilibrium. In our experiments, usually you might need to wait up to 15 minutes. And then once you've waited that long, measure their absorbance and percent transmittance through the spectrophotometry instruments. And what we're going to end up is, for each of our solutions, the initial concentration of iron is going to be 0.001 molars. The initial concentration of iron or of thiocyanate, that is going to depend on how many milliliters we take from that 2 times 10 negative third molar stock solution. Whatever we do, multiply those two numbers and divide by 10. That's the concentration value that goes there. And once we, at the very moment that we first have these two in solution, there is no iron thiocyanate complex that is formed yet. So initially its concentration is 0 molar. Because this is a 1-to-1-to-1 reaction, the reactants that will be decreasing in concentration will be -x for the change, and iron thiocyanate will increase with +1x for our change factor. And then at equilibrium, those are just going to be the first two rows added together. So iron 3 plus will be its concentration once equilibrium is established will be 0.001 minus our X factor. Thiocyanate will be its initial concentration minus X, and then at equilibrium, the iron thiocyanate concentration will just be equal to our change factor. What's very nice is that change factor is the equilibrium concentration of iron thiocyanate. That happens to be equal to the X value from our calibration curve trend line. Therefore, if absorbance equals the slope times X plus B, solving for X, we can, for each solution in part 2, quickly calculate its change factor by just taking the absorbance that is measured during that trial, subtract the y-intercept, and divide by the slope. That will get you your change factor, which is equal to your equilibrium concentration of iron thiocyanate. Therefore, you can also use that to determine the concentration at equilibrium of iron 3, which is just 0.001 minus that change factor, and similarly determining the equilibrium concentration of thiocyanate anion. And to get KEQ, all we need is the equilibrium concentration of our product complex divided by the product of the concentrations of our reactant ions, but specifically their equilibrium concentrations. And that should help us get to our equilibrium constants, dissociation constants for iron thiocyanate. Partway in your report, in your data sheet, you will be asked about a percent transmittance absorbance relationship. Here's the answer to that. Essentially, a percent transmittance is just your incident light your light that passes through the sample divided by the intensity of light that initially leaves your lamp in your spectrophotometer multiplied by 100%, and absorbance is just log or log base 10 of your full intensity divided by what makes it through your sample. Essentially, we have I naught over I, or I over I naught. We can just take the percent transmittance divided by 100 and do the inverse of that to find our ratio of I over I naught. Therefore, plugging that in, we can quickly relate absorbance and percent transmittance as absorbance equaling log base 10 of 100% divided by percent transmittance. Your instruments will be able to switch between one or the other. Therefore, you'll be able to quickly record both, but if you are only given either absorbance or percent transmittance, here is an example relationship you would be able to use. In any case, that concludes this lesson on our colorimetric determination of an equilibrium constant for our experiments. In any case, peace